Okay, in this video I'm going to talk about the Gauss-Seidel method for solving systems of linear equations. Some important fact about the Gauss-Seidel method. It is an approximate method. That means it's not exact, like Gauss elimination. So it gives a numerical answer. The other important characteristic is it's much faster than Gauss elimination. So that's why it's useful. Another important characteristic is it doesn't always work. Right. And this faster is very important characteristic. If you have large systems of equations with, say, 1,000 unknowns, Gauss elimination is impractical, and you need to use some approximate method like Gauss-Seidel. Okay. So what's the reasoning behind Gauss-Seidel? Well, let's start with our system of equations here. Suppose we solved the first equation for x1, the second for x2, all the way up to the nth for xn. If we did that, we would algebraically rearrange these equations one by one, and the result would be as follows. You can do this exercise. If I rearrange the first equation above and solve for x1, I obtain this equation for x1. Similarly for the other x's. I can rewrite that in summation form as follows. Notice this j unequal to 1. This summation does not include the j equals 1 term. This summation does not include the j equals 2 term, and so on. Okay, so my strategy is going to be something like this. I can't use these equations exactly because I don't know the x's. This gives me x1 in terms of the other x's, but I don't know the other x's. So I'm going to start with an approximate guess for the x's. And then I'm going to cycle through these equations. First, I'm going to update x1 according to this equation here. Then I'll update x2 according to this equation here. And I'll update all of my variables according to the last equation there. And I hope that at this point, my approximation has been improved. Now that's the rub. For some matrices, it won't be improved, but for a certain class of systems of linear equations, you do in fact get an improved solution. Okay. Once I've done this update and I've updated all my variables, I'm going to repeat. Okay, and I'll keep repeating until my error is smaller than a certain tolerance. Okay, now in the chapter here, he talks about the relative error. I'm a little bit suspicious of that because of the value of x in the denominator. If, for example, my solution actually has one of the x's equal to 0, then I'm going to have a large relative error. So I'm not going to use that. We're going to use just the error itself, which is xi new minus xi old. Now this is not the actual error, this is the approximate error. And I want to make sure that all of my x's are fairly accurate, so I'm going to take the maximum over I of all of these differences between my new estimate and my old estimate. And if that's less than my error tolerance, then that will be my stopping criterion. In other words, I'm going to keep on doing this cycle, update, 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 update all the x's, update again, until my error is below the tolerance as indicated here. Okay, well, let me go quickly through the rest of this document. Here, an example is done where Gauss-Seidel method does not work. If you go through this example, you'll find out that it doesn't actually work. It's not getting closer and closer to a solution. The errors are not becoming smaller. The key is that you can only apply Gauss-Seidel in cases where the matrix is diagonally dominant. Diagonally dominant means that you have a matrix of coefficients where the entries on the diagonal are much larger than the entries off the diagonal. In fact, the condition is this, that the diagonal element AII is larger than the sum of the absolute values of all other entries in that row of the matrix. And that has to be true for every diagonal element. So for instance, eng1 needs to be larger than the sum of the absolute values of all of these entries. eng2 must be larger than the sum of the absolute values of all of these entries, etc. If you have a matrix in this situation, then the Gauss-Seidel method will converge, and will converge very quickly. All right. Notice here that we do satisfy the diagonal dominance condition because we have eng1 equals 12, which is greater than absolute value of 3 plus absolute value of 5. Here we have eng2 equals 5, which is greater than absolute value of 1 plus absolute value of 3. Where am I getting the 1 and the 3? Though there are these other coefficients here, 1 and 3. And we also have eng3 equals 13, which is greater than absolute value of 3 plus absolute value of 7. Okay? So in this case, we do have a diagonally dominant matrix. So our system of equations satisfies the necessary conditions for a Gauss-Seidel method to work. And here he goes through and shows that after certain iterations, after the first iteration, it's large, so the percent error is going down. You can see after only 6 iterations, we have a percent error of less than a 1,000th of a percent, or about 1,000th of a percent. Okay. So that's an example of how Gauss-Seidel works. In the next video, I'll show you how to program it in Scilab.